In this video, I am going to go through the thought process that you can use to synthesize a targeted organic molecule using reactions that we have learned so far in Organic Chemistry 2 or also in Organic Chemistry 1. Keep in mind as we go through this video that although I am going to provide you with one way and one thought process for creating the targeted organic product, that with synthesis projects, there are generally multiple routes to the correct answer because there are generally multiple reactions that will yield the same or similar products. Like we learned multiple ways to go about reducing ketones to yield alcohols, for example. So we will go ahead and take a look at this example problem. I'll show you a thought process to design a chemical reaction. So we'll take a look at this example problem. It has some wording that's pretty typical of the types of synthesis problems that you might encounter in this course or elsewhere, which is that we are asked to provide a route or a way to synthesize the molecule that we have here as a major organic product of a sequence of reactions. Now we have to keep in mind our limitations. These limitations would be imposed by what we have easy access to from a chemical vendor or perhaps sitting around the lab already. So in our case, we are going to limit ourselves to we can only use as our starting products benzene, any phosphorus ylide, any compound with 2 or fewer carbon atoms, and whatever inorganic reagents or materials we need for these syntheses. So what we're thinking about here is if we need to build something that is other than any of these 3 types of compounds, benzene, phosphorus ylide, or something that has 2 or fewer carbons, we're going to have to find a way to create that ourselves, starting from one or more of these components. So in other words, we're pretending that the lab we are working in only has access to benzene, phosphorus ylides, and compounds with 2 or fewer carbons. And we have to find a way to construct from those sorts of building blocks whatever final product we are aiming for. In this case, we're aiming for this product here. So here's how we want to approach this as a general thought process. You want to try to break the molecule up into bite-sized portions, if you will. That is, parts of the molecule where you can think about how you would go about synthesizing that particular part of the molecule from the desired starting material. So in the case of the aromatic ring that's directly bonded to the bromine, for example, just thinking one step at a time so as to not get overwhelmed, we say, how would we go about making an aromatic ring with a bromine on it? Well, we learned about electrophilic aromatic substitution reactions back in an earlier chapter. And in those, what we would do is we would take benzene, which we are allowed to use as a starting material because the directions said benzene was one of the things we had access to, and we could react that with bromine, Br2, and iron catalyst, iron tribromide, for example, to give a product that had that bromine substituent. So this is one of the reactions that we will want to potentially incorporate into our scheme here. So we would use an aromatic molecule as our starting material, react with bromine and iron to give our product. We have to decide what order this reaction is going to fall within the grander scheme of things as well. But for now, I'm just focusing on this little part of the molecule, dissecting it, and thinking backwards, okay, from here, what could we have done to create that bromobenzene group? Then we come to this other portion of the molecule here, our aromatic ring directly bonded to this alcohol group. And we say, how can we go about making that alcohol group off of an aromatic ring, given the limitations that we face here? And there will generally be a few ways to go about doing things. So the way I'm going to show you right now as I think backwards about this may be different than what you come up with. And definitely there's not one right or wrong answer to this. So as I think about this and I think backwards, I'm like, what ways do I know to create an alcohol product? Well, thinking generally, there's a bunch of different possibilities. But one way I think of is that you can do a reaction where you start with an alkene, and you do an addition reaction to give an alcohol product, such as acid catalyzed hydration, which would be reacted with H+, and with water. That would follow Markovnikov's rule. Or alternatively, to go opposite Markovnikov's rule, you could do hydroboration oxidation, BH3, first, followed by peroxide for the oxidizing agent and base. And that would be a way also to give an alcohol product from alkene, and these two different approaches, acid catalyzed hydration and hydroboration oxidation, give opposite regioselectivity so that we could tune the reaction to give the hydroxy group at the correct position by deciding which of these two routes to use. So that's a general way to go about making an alcohol out of an alkene. But if our starting structure here is an alkene, like we had an alkene group right here where I'm highlighting with a laser pointer, and we did the addition, that would get us to the last step, but we need to think further backwards, because in thinking further backwards, as we work our way backwards, we need to think about how can we make that alkene. This alkene group that we would need to be using here to make the alcohol out of has more than 2 carbon atoms. So we can't use an alkene as our straightaway starting material. We have to use something else. And so we ask, how can we make alkenes? Well, one way we learned to make alkenes that also gave us a new carbon-carbon bond was to react a phosphorus ylide with an aldehyde or ketone. And this was a really useful strategy because that not only yielded an alkene group, it also made a new carbon-carbon bond. So that's going to help us stitch together the pieces of the molecule to ultimately create our final product. So we might be saying to ourselves, well, what phosphorus ylide and ketone, aldehyde or ketone could we use to do this? And so we have to think about what the actual structure of the molecule would be at that point. But keeping generic here, I'm going to step back another step here. Rather than filling that in specifically at this point, I'm going to say, well, how would I get an aldehyde or ketone associated with the aromatic ring? And one way we could do that is by the Friedel-Crafts acylation. So we could take benzene. We could react it via Friedel-Crafts acylation with an acyl halide rather. So like acetyl chloride right there with aluminum chloride catalyst. And that would result in attaching the ketone group to our aromatic ring. And then from there, if we react with a phosphorus ylide, we'd be reacting a ketone with a phosphorus ylide, that would give us our alkene, and that would take us onward to our alcohol. So we need to think about going about doing this and what order we would put the reactions in for this. So I'm going to, in continuing our progression toward the final answer for this, as some trial and error and scratch paper work that would be going on here as you go through your thought process for this, I'm going to sketch out and ask myself, how would I make this specifically? Focusing on just that aromatic ring directly bonded to our alcohol here, like so. So how would I go about doing that? And then we'll try to merge that with the simpler half of the molecule here, simpler in terms of number of reactions required, that we can just do an electrophilic aromatic substitution to bring in the bromine. So creating this group from the starting materials that we have at our disposal, we say, okay, well, we could start with an alkene, because we know in our general schematic here that we're able to take an alkene and convert it into an alcohol with a couple of different possible regioselectivity options. So the way that this would work is we think back to what is the case when we were dealing with addition reactions. And when we were dealing with addition reactions, the way it worked was that we would have an alkene, we would add H and OH across that carbon-carbon double bond to give an OH on one carbon, H on the other. And so this alkene group has the same carbon skeleton as our final product. We just bring in that alcohol group. So how would we go about doing that? Well, how we would go about doing that is via either hydroboration oxidation or acid catalyzed hydration. We have to decide which one to use here. So we ask, does it follow Mark's rule, meaning acid catalyzed hydration, or does it go opposite Mark's rule, meaning hydroboration oxidation? This is where being fluent in the reactions comes in really handy. So we are going here in a way that is opposite Markovnikov's rule, and so therefore the correct reagent to use would be to first bring in borane BH3, secondly, bring in the peroxide, and the sodium hydroxide, and that would give us the addition reaction with the appropriate regioselectivity. We're not quite back to where we need to be yet, though, because what we started with here definitely has more to it than just benzene, phosphorus ylide, or 2 or fewer carbons. We've got a pretty complex molecule going on there. So we need to break that down further. And that's where we look back at our general flow chart here, where we said, okay, we know that we can take a phosphorus ylide and an aldehyde or ketone and make an alkene out of it. So to make this now specific alkene, how do we go about doing that from a phosphorus ylide and an aldehyde or ketone? Well, the aldehyde or ketone we could start with here would be an aromatic ring directly bonded to our ketone group. That would correspond to this part of the molecule here. These 2 carbons that I'm highlighting in red in our product are what go along with these 2 carbon atoms of our starting material. When we react that with a phosphorus ylide, thinking back to that reaction of aldehydes or ketones that we learned just a couple videos ago, the way that this will work is that we have our phosphorus ylide, which is phosphorus bonded to 3 phenyl groups. That phosphorus is also bonded to a carbon, which acts as a carb anion. And that carbon has groups that we called previously generically A and B. A and B represent, in the schematic of how that reaction, the Wittig reaction as it's called, works, is that the 2 groups that are here are going to correspond to the groups that we have bonded to the carbon and the phosphorus ylide. So we have a methyl group and a hydrogen. So I'm going to plug in a methyl group and a hydrogen here. And what happens in this so-called Wittig reaction, which I'm just going to scribble out Wittig reaction here so that you have a reminder of what's going on. What's going on is that the carbon and the groups that the carbon is directly bonded to, that is everything other than the phosphorus, are going to come in and be attached up here where the carbonyl originally was. So the carbonyl oxygen specifically was originally here. Carbonyl oxygen is replaced with the carbon and the methyl and hydrogen through that Wittig reaction that we learned the mechanism for a couple of videos ago. And then the other portion of the molecule will be the aromatic ring with the 2 carbon chain. That's going to correspond to the aromatic ring up here, 2 carbon chain. And so the Wittig reaction has made that new alkene group. So that gets us a bit closer to the start line for this reaction because our directions so that we can use any phosphorus ylide. So we're good to go there. We can use this phosphorus ylide that I'm circling as a starting material, even if it has more than 2 carbons, because we can use any phosphorus ylide here. So now, taking a step further back, we select our ketone starting material here. And we think back to reactions that we learned for aromatic compounds. And looking back in our flow chart here, a general diagram, we said that we could take benzene, do Friedel-Crafts acylation, and attach that acyl group onto it. So that's what we're going to sketch out here as doing. Start with benzene, react with our 2 carbon acyl chloride, aluminum chloride catalyst, like so, and that is going to enable us to create our targeted product here. So we've got our aromatic ring, and we brought in the 2 carbon acyl group. That's our 2 carbon group here that I'm highlighting in green now to give us this. And these 2 starting materials, our acyl chloride and our benzene, are both acceptable starting materials because the directions say anything with 2 or fewer carbons. So therefore this acyl halide that I'm circling qualifies and benzene will work. So now we've got a route to go from 2 carbon starting materials all the way through to this final structure that has the alcohol and alkyl branch coming off of it. We also need to bring in that bromine. So we have to decide what order to do these reactions in order to get the proper substitution of the aromatic ring. Now, thinking about directing groups, we know that the alkyl group here should be a ortho-para director because the oxygen here that's electron withdrawing by induction is pretty far away, so it's going to have a very, very weak inductive effect when we think all the way to the ring. And there's lots of alkyl group here, so by induction, we would expect that this group is electron donating and therefore activating. And so what we can do here is we can, as our last step of the reaction, we can take that product that we've created here that I'm highlighting, and we can do our bromination on that. So we take Br2 with iron or iron tribromide as the catalyst, and that's going to enable the formation of that substituted product. So we'll go in like so. And based on electronic effects, we would expect that the bromine would occur at the para position and at the ortho position. I will say that in reality, if we were considering steric effects as well, that this product that I'm drawing that is ortho here would probably not be the favored product because of the fact there's a lot of steric hindrance from this bulky group that I'm circling that prevents the bromine from coming in there. But by electronic effects, we expect those two possible products, of which the one of interest is the one that I'm circling in pink right here. That structure matches our final one. So in total, what we've done is gone through this series of reactions that I'm putting in a yellow box here to go from begin reaction 1, reaction 2, 3, and 4 to enable us to synthesize the targeted organic molecule as our major organic product. And this is something that you will commonly be tasked with doing, not only in this class, but also if you pursue any research or future jobs in the field of organic chemistry where you're doing synthesis. Designing chemical reactions is a common skill, and it's also a useful skill just from the perspective of organic chemistry because it really forces you to think creatively and critically about what reactions we know and how we can stitch those together to solve a puzzle. So you can really think of the final organic product as being the puzzle to solve, and you have the parts and pieces that you have to assemble together, much like putting together a bunch of Legos to make a particular object. You have to think about what order you can logically assemble those Legos or those individual atoms and groups in, following based on what building blocks you have access to, which is listed here in the problem.